We begin our discussion about right triangle trigonometry. So far we've been dealing with unit circles and have really dealt very little with triangles. And some of the applications, some of the problems we work on will have to do with triangles. The unit circle business is really where we focus most of our attention when we're in calculus, but certainly it would be not to our benefit to ignore the applications that involve triangles. So that's where we begin today. Now, as you recall that a right triangle is a triangle that has a right angle, and that is an angle of 90 degrees. And anytime we have a right triangle, you notice I've illustrated that the 90-degree angle, the right angle, is right here. Then the side that is opposite that right angle is called the hypotenuse. And for this discussion, we'll use the abbreviation HYP for the hypotenuse, but specifically for the length of the hypotenuse. And you see I've indicated one of the other angles in this right triangle is angle A. Okay. Now, so when we're talking about an angle A in a right triangle, of course we have a right angle and we have two other angles. And so some of the terminology we have to get used to is when we say the side opposite the angle A, then of course we're talking about one of these two legs. And of course opposite of A is this side over here. So you'll see me refer to OPP as opposite, and that's the length of the side that's opposite of the angle A in this case. And then we have this side, and this side is said to be adjacent to the angle A. This is opposite, this is adjacent, and of course this is also adjacent, but it's specifically the hypotenuse. And when we're talking about the adjacent side to an angle A, then I'll refer to its length as ADJ. Well, here's the whole issue about these right triangles. We can talk about the sine of an angle that is in a right triangle. We can talk about the cosine of an angle. We can talk about the tangent of an angle. And of course, all of the 6 trigonometric functions we can have of an angle. And so that's in a right triangle. So we define the sine of the angle A in a right triangle as to be the ratio, the length of the side opposite of angle A divided by the length of the hypotenuse of the right triangle. And in a similar fashion, we define the cosine of the angle A in this right triangle as the ratio of the side that is length of the side that is adjacent to the angle A divided by the hypotenuse of the right triangle. Now, because of the relationship between tangent of an angle being the sine of an angle divided by the cosine of an angle, it's not difficult to show with the definition of sine of A and cosine of A that the tangent of A ends up being the ratio, which is the length of the side opposite of A divided by the length of the side adjacent to A. Now, we could do this just by performing the division of these two fractions, but we'll remember that definition. So these seem to be, and by the way, we can get the other 3 trig functions in a similar fashion. We can define them in these ways, but I have a hard time remembering these. I want to pay attention to the 3 that we've got down here, the first 3. Sine of A is opposite over hypotenuse, cosine of A is adjacent over hypotenuse, and tangent of A is opposite divided by adjacent. Now this seems to be brand new. This seems to be unlike what we did, of course, with the unit circle, how we define the sine of an angle A, and we'd have to decide, we'd find out where that angle A terminated, and then we'd find the point on the unit circle. And so the sine of the Angle A would be the y value of the point on the unit circle that's associated with it, and so on. So it seems to be unlike what we've done previous to now. But let me show you on the next slide that it is equivalent. And this is really just to convince you that we're not changing the rules, we're just seeing the rules in a different, through a different set of glasses now. So let's imagine that we take that same, pardon me, that same right triangle and lay the adjacent side of the right triangle along the x-axis, where the vertex of angle A is at the origin. And so, of course, here we have the hypotenuse, and here we have, of course, the other leg of the right triangle. Now, under these circumstances, this position of where this hypotenuse and this vertical leg intersect could be labeled as a point that is in the xy plane. We'll say it has an x value of x and a first coordinate of x and a second coordinate of y. And of course, this is the distance x, okay, from here to here, so that's the x value. And from here to here, this is the distance y, so that's the y value. And we'll label for now the distance from the origin to this point as length r. The length of that distance is r. Now, of course, earlier we called this hyp, but just to get into a new swing here. Now, if you recall, when we first started talking about the trig functions, and we started out with a unit circle, and then we expanded to the idea, a long time ago it seems like now, we expanded to the idea where we said, okay, we've got an angle, we've got a terminal side of an angle and a point on that terminal side. How do we define the sine, cosine, and tangent of the angle that has that terminal side? And what we decided that we would do is we'd say, oh, okay, and we showed this with similar triangles basically in the unit circle is what we ended up doing. But we said, okay, well, under those circumstances, the sine of said angle A would be the y coordinate divided by the distance from the origin to the point. So that would be y over r, y over r. See, that's how we defined that early on. But y is nothing more than the length of the opposite side, and r is nothing more than the hypotenuse. So y over r and opposite divided by hypotenuse are equivalent. And we also decided that the cosine of said angle would be the first coordinate of the point that is on the terminal side divided by the distance from the origin to that point, which is r. And so we decided the cosine would be, in this case, x over r. And of course, x is nothing more than the length of the adjacent side, and r is the hypotenuse. So x over r is the same thing as adjacent over hypotenuse. And we could go through the same argument for the tangent of the angle A. At that time, we said, well, it would be the second coordinate divided by the first coordinate. And the second coordinate being y is the same thing as the opposite of side A, of angle A, and x is the same thing as adjacent side, length of the adjacent side. So y over x is still the opposite over adjacent. And we could go through the rest in this fashion. So what we're defining here in terms of a triangle is equivalent to what we have done in the past. It just looks different. Well, let's use these things then to talk about how we solve a right triangle. And here's what it means to solve a right triangle. It means to find the measure of all the angles and sides of the triangle. Well, there are 3 angles and there are 3 sides. And so when we're done, we have to know the length of all 3 sides and the measure of all 3 angles. Of course, one of the angles is a right angle, and so it's really just find the measure of the other 2 angles. So I've illustrated, and by the way, it is common practice when we're dealing with these to label the angles by capital letters. And it's common practice that we label the right angle as a capital C. Okay. Now we label the sides with lowercase letters, and we label the side that is opposite angle A as side A, length of side A. A represents a length. And we label the side opposite of angle B lowercase b. So that's, you see that relationship. And of course, we label the hypotenuse lowercase c, and that's opposite the angle C, which is the right angle. So it's not unusual that we see this scenario. So here we have a right triangle that is given to us. And here's what we know about that right triangle. Angle A is 34.2 degrees, and side B is 19.4 units long. So to solve this triangle, we need to calculate three more things. We know angle C is 90 degrees. We need to find side C, that is the length of the hypotenuse. We need to find the length of side A, and we need to find the measure of angle B. So there's really three pieces of information we've got to gather. Well, the first thing for us to do here is that we can easily calculate the angle B. What we know is when we add up the angles of any triangle, we get 180 degrees. And one of the angles, this angle C, is already 90 degrees. And so the other two angles have to add to the additional 90 degrees. So angle A plus angle B has to be 90 degrees. Now, in this case, we already know what angle A is. So if we want to know B, we take 90 degrees and subtract A. And that's what I've shown here. Angle B is 90 degrees, subtract the length of angle A, 34.2 degrees, and when we do that calculation, we get 55.8 degrees. So now we know angle B, we've got to work on side A and side C. Well, we need to kind of get through a pattern here and understand where what's taking place. Whoops. We need A and C. What do we have? We have angle A and side B. So for instance, if I'm wanting to calculate the length of angle A, I've got to have an equation that has that value in it, the unknown value, plus values that we know. And so we need to figure out which trig function involves what we're looking for and what we have. Now, of course, the angle is 34.2 degrees. So the question is, do we use the sine of an angle of A? Do we use the cosine of angle A, or do we use the tangent of angle A? Of course, the sine of angle A is opposite over hypotenuse, and we don't know either A or C, so that won't help. The cosine of angle A is adjacent divided by hypotenuse, and we're looking for side A, so that isn't useful right away. But if we look at the tangent of angle A, that's the opposite divided by adjacent. So the only unknown is the opposite, and that's A. So that's the reason I've made this decision, is that I'm going to use the formula that the tangent of A is equal to the side opposite of A divided by the side adjacent to angle A, which is A over B. I know angle A and I know side B, and so this is going to be useful. Now, before I go through all the work, though, I'm going to take this formula. I'm wanting to know what A is, and so I'm going to take this formula and I'm going to multiply both sides by B. That will leave A alone, and it will give me B times tangent of A. So A is equal to B times tangent of A. All I did is multiply both sides by B, and then I turned it around. So here's where we are. I'm looking for A, I know B, and I know angle A. So I actually put those values in here. Okay. In fact, let me pause and get my calculator out and show you how I've done this. Okay, you can see I've got my calculator out now. And notice what I've done already. Pardon me. A is equal to length of B times tangent of angle A. And of course, the length of B is 19.4 units, and angle A is 34.2 degrees. And so I just need to do the calculation. Now, I've actually shown the result here of finding the tangent of 34.2 degrees. But one of the things that I need to remind you of here, see if I can expand. It doesn't look like I can expand that size like I want to. We've got to make sure that we're in the correct mode. And so as I go to the mode key, which is right here, and I'm needing to decide, oh, look, on this third line, it's set to radians. But I'm going to put in a angle in degrees. And so I need to scroll down and across to where I have degrees and press enter. And now I can leave the mode function by saying second quit. And now I'm back to where I need to be. So just as an example then, if I was calculating the tangent, here's the tangent key, of 34 point, now I know it's degrees, 34.2, it's going to interpret it as degrees, and press enter, then that's this 0.679599298. Looks like I left off a 2 here, okay? But I really want my calculator to do the whole job at one time. So what I'm really going to say is 19.4 times the tangent of 34.2 degrees. And it already is expecting it in degrees, and press enter, and see it gave me 13.184 and so on and so on. Now, let's make sure that we understand I rounded this off to the tenths, 13.2, and you can see that's the way that would round. I rounded to 13.2. And I got my hint from the information I had about the other side was only to 4/10 accuracy. Okay, so I can't have this side more accurate than the given information. And so that's the reason I've rounded it to the tenths position, 13.2 units long. Okay, well, let's move now. What do we know at this point? We needed to find out angle B. We need to find the length of, and we did that. We need to find the length of A, and we've done that. And we need to find the length of angle C, of side C, which is the hypotenuse. So that's the next thing we need to consider. Oops. Now, to solve for that side C, we use this fact. See, now here we are again. We would like to use this information to find C. And so we look at, well, what is the relationship between this angle and the adjacent angle and the hypotenuse? Well, what function does that involve? It involves cosine. The cosine of an angle is the adjacent side divided by the hypotenuse. And the adjacent side is B, and that's information that's given to us. And the angle A, we know, we're looking for C. And so it's appropriate, that's the reason I'm choosing to use the cosine function. Cosine of A is equal to B over C. And I know angle A, I know side B, and so I can go about my business. Well, I need a little formula for C, so here's what I've done. I've taken this cosine of angle A is equal to B over C, and that's adjacent divided by hypotenuse. And what I did is I took this equation and multiplied both sides by C. I'm trying to solve for C, so I'm getting it out of the denominator. So I have C times cosine A is equal to B. And so then I divided by cosine A on both sides, so I get C is equal to B divided by cosine A. That's where this came from. And so now I'm prepared to put my information into this equation, and I was given that side B is 19.4, and I was given that angle A is 34.2, so I simply put that into my calculator, and I get 23.5, and I also rounded this to the 10th position because I had no more accuracy than that to begin with. And so now we have accomplished what we set out to do. We now know the measure of angle B. That was one thing we needed to know. We now know the measure of side A. And lastly, we know the measure of side C, the hypotenuse. So we've completed the solution to this right triangle. Now, there may have been some thoughts that you had while I was doing that, so I want to go over a few guidelines to make it clear some things that we need to be careful of. In the last position, when we were finding side C, whoops. Well, I blew this. Okay. I see my slide is inaccurate. In each case, it is important that we use a relationship that involves the unknown we're trying to find and two known items. Now, what we did is we used the cosine of A is adjacent over hypotenuse, not the sine of A. And so we knew angle A, we knew side B, we didn't know side C, and that's what we were looking for. So this should say cosine of A, my bad. Now, you might have thought about this. Oh, yeah, see, here's where I screwed up. What I really meant to say here is that we could have used, you may have asked, why didn't we use sine of angle A is equal to opposite over hypotenuse? Because we had already calculated the length of the opposite side. But here's the reason that I chose not to do that, is the length of the side A was a calculated and approximated value. And so if we had an A in this position, although we know it now, it would have been an approximation. And so our preference is to use given information to calculate the unknown information. Otherwise, we're going through approximation versus on top of an approximation. Now, the same thing can be said is, well, we knew side B, we had a value for side A that we calculated, and so to find side C, we could have also used A squared plus B squared is equal to C squared. But keep in mind, A was a calculated value that was an approximation. Now, B was a good known value. We expect that to be completely accurate. So we would have used an approximation to calculate C, and we wanted to rule that out. When we used what we did, the length of B was a given and the angle A was a given, so there wasn't any issue about approximations. And then about the rounding, and I said earlier to use the same accuracy, the number of decimal places as given in the given information. And if similar information is not given, calculate lengths to the nearest tenth and angles to the nearest hundredth. If you don't have given information that's a length, then just assume to calculate it in terms of to the nearest tenth. If you're not given any angles, but you're calculating an angle, then make sure you calculate the angles to an accuracy to the nearest hundredth. But usually you take your hint from the information that's already given and not to have something any more accurate than given information. Okay, so let's start from scratch and do a brand new problem. And this problem, as you can see, says to solve the right triangle ABC, and that's referring to the angles A, B, and C. We understand C is the right angle, okay, right triangle. If side A is 29.43 units long and side C is 53.58 units long, that means we need to come up with angle A, angle B, and side B. Those are the three pieces of information we need. So it's useful to draw a sketch. Whenever we start out with something like this, if there's not already a sketch like there was in the last one, we draw a sketch. And so I've drawn a right triangle, and I've labeled the angles. Of course, the right angle is C, and I've labeled the angle A and the angle B. And if this is angle A, then the side opposite of angle A is side lowercase a. And of course, the right angle C, the side opposite it, which is the hypotenuse, we're told is 53.58. So we need to know angle A, we need to know angle B, and the length of side B. Now we have something to refer to. So we make a decision on what we'd like to do first. And one way to begin is to find angle A. Now, to find angle A, I need to use information. I don't know angle A, but I need a trig function that involves angle A and two pieces of known information. And the known information is the side that's opposite of A and the hypotenuse. And so that makes me think, oh, the sine of A is opposite of A divided by hypotenuse. And those are the two pieces that we know. So that is a perfect setup for us. Okay, that's a perfect setup for us. All we need to do then, okay, is to calculate the sine of A. We know is opposite, which is 29.3 of 0.43, divided by the length of C, the hypotenuse, which is 53.58. So we know the sine of A is approximately 0.5493. Well, what do we do next? That doesn't tell us what A is. Well, here's where we re-enter the idea of inverse trig functions. The angle A is the inverse sine of this number, or this result right here, okay? This number, which is, of course, an approximation to this. Because after all, if I take the sine of A, I'm supposed to get this number. And so in steps the calculator for us to finish this. I already know that I'm in degrees, and so it's going to understand what we're doing when we do this. And so A is going to be the inverse sine of 0.5493. Actually, it would be better to take the inverse sine of this fraction, but I'll just show you that they're similar. Turn my calculator on, and let me clear what we see there. Now, if you'll notice right, it's very hard to see, and as small as this is, but if you look at your calculator, above the sine key in yellow is SIN with an inverse 1 on it, okay? So this is the inverse sine key when we press second and then the sine key. So that's what I'm going to do. Press second, sine key, and so it's going to calculate the inverse sine of 0.5493, close my parentheses, and enter. So that's roughly, now we've said if we didn't have an angle to go by, we would round it to hundredths. So this is 33.32 degrees. Now, just to show you that we could have done this all at once, in fact, it may be a little more accurate if we do this. We'll say for the inverse sine, second sine, and now we're going to take 29.43 divided by 53.58. So 29.43 divided by 53.58. So I can, and then close the parentheses. So I can make the calculator do all of my work. And notice that this is actually a little more accurate but if I round to hundredths, I'm still going to get 33.32. And I think that that's what I'm showing here, 33.32 degrees. So now we know angle A. What do we still have to find? Angle B. But once we know angle A, angle B should be easy because A plus B has to be 90 degrees. A plus B plus C is 180 and C is already 90. So A plus B has to be 90 degrees, so B is going to be 90 degrees minus A. And so that would be the easiest thing to do next. As I already said, A plus B is going to be 90 degrees, and so to find B, we take 90 degrees and subtract A. And when we do that, of course, it's 90 degrees, subtract 33.32 degrees, and that calculates to be 56.68 degrees. So now we know angle A, we know angle B, we know side A and side C, they were given, we need to find side B. Now, to do that, here's what we don't want to do. Angle A and angle B, we have information about, but they're both approximated, if you will. Since A was approximated, B is approximated. And so we would rather come up with another way of finding side B without involving those approximated sides. Well, here's the situation. This is a right triangle. In a right triangle, A squared plus B squared is equal to C squared. And so we have an equation that involves two pieces that are given as known and one piece that is what we're supposed to find and calculate. And so that's what we're going to do here, is we're going to use the Pythagorean theorem, A squared plus B squared is equal to C squared, to find B. So I've just turned that around. C squared is equal to A squared plus B squared. And actually, I guess I've done that backwards. I've got an extra step in there I don't need. If I want to know B, I'm going to solve for B squared by subtracting A squared on both sides. And then I know B is the square root of the right side. Since B is a length, it's not going to be negative. And so I simply put my 53.58 in for C, which is a given, and I put my 29.43 in for A, which is a given, and when I calculate, then I will get 44.77. Now let me just show you how I've done that. We'll clear. Whoops, it's not a graph. Clear, okay. And once I've got this set up, then I use my calculator at this level only. So I'm going to start out with square root, which is second x squared here. So okay, it opens up parenthesis, and then I'm going to put in 53.58 squared. Well, here's a square key. That's real easy. And add to that 29.43 squared, and then close my parentheses for the square root, press enter. Oh, I've made a mistake, haven't I? Let's see, what did I do? You see where I made my mistake? I put plus. I put plus instead of minus. Remember, our formula had a minus. Now, this actually brings up an issue. And so let me point this out while we're here. If I wouldn't have already had the answer and not noticed, okay, that I put a plus, then I should be alerted. And here's why I should be alerted. I've got B as 61 point something units long. And the longest side on a right triangle has to be the hypotenuse. So B certainly could not be more than 53 units long. It couldn't be 61. And so, oh yeah, that's a bad issue here. So let me go back. Can I change this? Let's see. What do I do? Let's see. Okay, if I press second and enter, I get that same equation back. And now I'm just going to scroll back and delete that plus sign and put a minus sign in there. Whoops. Well, I blew that, didn't I? So I'm still going to have to work. Um, let's see if it's very hard to see, isn't it? Where do I enter? Can I press, where's an enter key? I wish you were here so you could tell me. I can't see it on my calculator. Insert is actually what I'm looking for. I said enter, oh, right here, okay. So second, and now I'm going to put a 2 in right there. Okay, that's just saved me a little bit of work. And now we press enter, and we get 44.7737, but our size were already given to us to the accuracy of 1/100th, and so we'll round this off to 1/100th. We look at this 3, and so we just truncate. We don't round up. So that's my 44.77. Okay. Well, let's see what's in store next. We'll move to the next problem. And this one's actually an application. So I've got a beginning to this before we get started. And it says generally in problem solving, sometimes the process of solving right triangles is a step necessary to solving an application or applied problem. And a crucial step in solving these application problems is to sketch the triangle and label the given parts correctly. So sketching is something we do a lot in trigonometry and actually in other courses as well. So here's our problem. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. If a fire department's longest ladder is 110 feet, what is the maximum safe rescue height? Oh, well, before we draw anything, it says the maximum angle of elevation. Now, maybe that's clear what that is, but I thought maybe I should say something about it before we move on. And so here you can see the term angle of elevation represents the angle from the horizontal upward to an object. So here we are as an observer, and horizontal to us, we've got this. The angle of elevation would be like the angle of the eyesight to the object that we're talking about. And so that's the idea of angle of the elevation. Now there's also a term called angle of depression. And so for objects that lie below the horizontal line of sight, now it may be up in the air, but we're thinking of the observer being horizontal to, looking horizontally. And if the object is below the observer or this horizontal sight line, then we call that angle the angle of depression. Okay, so if it's going up, it's angle of elevation. If it's going down, it's angle of depression. Okay, well, let's get back over here and let's see if we can't sketch a graph. I'm kind of proud of my graph. Okay. Now, what we're going to do, and by the way, what I've done here is we've got a fire truck. It's got a ladder on it. We've got a building. I've just illustrated that. The length of the ladder is 110 feet long. That says the fire department's longest ladder is 110 feet long. The angle of the safest angle of elevation is 72 degrees. And so that's going to be this angle off of the horizontal. Let's think about this amount of distance to the top of the fire truck as being negligible. I mean, we could measure this distance as well to get the total safe rescue height. But what we're really looking for then is the length between this horizontal where the ladder lays down flat to when we have the ladder extended 72 degrees, its maximum amount, then what is this distance? So we're looking for this distance A, and then maybe we could add the extra piece down here, but that's not part of this problem. So if you notice then, this ends up being the hypotenuse, and of course this horizontal alpha of the truck is a leg, and this vertical along the building is the other leg. And so I'm calling this angle, this maximum safe angle, 72 degrees, this angle A. And of course this is going to be the right angle, so I've labeled it C, and the angle with the ladder in the building up here is angle B, and of course the hypotenuse is 110 feet long, and this distance that I'm looking for I'm calling lowercase a because it's opposite of this angle A. So what I need is I want to find a, lowercase a, and so I need a relationship between this side, the hypotenuse, and this angle. And so I need something that involves angle, opposite, hypotenuse. And that should have us think of the sine is defined. The sine of an angle A is defined as the opposite side divided by the hypotenuse. In this case, A divided by C. Opposite divided by hypotenuse. And I'm looking for A, so I take this little equation, just multiply both sides by C, so I get A is equal to C times sine of theta. And I know C, this length, and I know angle A, 72 degrees, and so I just insert those in. And when I do this calculation, I get 105. And so that's actually 105 feet, isn't it? That's a length. And like I said, if we knew the distance between the ground and the horizontal levelness of the ladder off the truck, we could add that in. But we're going to assume that's negligible. Okay. You know, I don't know what it might be, 3 or 4 feet, but we'll assume it's negligible. We're looking for this distance. And so we've actually completed the problem now. So the maximum safe rescue height is about 105 feet above the height of the fire truck. I qualified it here, above the height of the fire truck or the bed of the fire truck. Well, that's all of the information in this introduction to right triangle trigonometry. Next, we have in the next lecture, there are some more application problems. That is, word problems that involve right triangles, and they get a little more complicated than the one we just did. So good luck on the first part of the homework, but make sure you look at the second video so you can do all of the homework.